Welcome, welcome. This segment is on how to do sex-linked traits with their Punnett squares. Lots of letters, lots of exponents, superscripts, carets, whatever you like to use. Mine is on paper. I think it's easier for me to kind of explain what's going on, see how I write it as I write it, instead of just looking at a screen with me typing on stuff. So that's why I have some paper down in front of me. If you want to do it on your computer, great. If you want to print it out, do it along with me, that's fine too. All right, let's get started. So sex-linked traits, this is pages 10 through 11 on the document in the comments. Here we go. So all of the following are sex-linked recessive disorders. So when we see this trait expressed, that means it is recessive. So it must have the homozygous recessive or little letter, lowercase letter attached to those sex chromosomes. All right, so here we have hemophilia. So a normal person has capital H because normalness is dominant, hemophilia is recessive. That'll get a little h because, again, it is recessive. Next, we have muscular dystrophy. Same deal, except we're going to use M for muscular dystrophy. And lastly, we have color blindness. Again, same thing. Normal is to be color seeing, and recessive is being color blind. All right, so get a little practice going on here. Write the genotypes for the following individuals. So we have a bunch here that we need to fill in. A female with no family history of hemophilia. All right, so we know these are sex-linked, so we're going to have to write in our chromosomes. If it's a female, we know she's going to have 2 X's for her sex chromosomes. So right away we can draw in an X for her first chromosome, and then we need to decide what do her alleles look like. Those alleles are going to be little tiny superscripts, or some people like to call them exponents. If you are working on your computer and you don't know the hotkeys, you don't want to go through the menus of formatting to superscripts, no worries. You can just use the little caret symbol of Shift 6. That kind of signifies, hey, this next piece is going to be considered a superscript or up in the top right corner. All right, so if we have a female with no family history of hemophilia, that means she's going to be normal. She's not going to be a hemophiliac because she doesn't have the gene for hemophilia because no one in her family has that gene. And if she's normal and she's not related to anyone who's hemophiliac, she's just going to have some regular capital H's. So up in the top, we're going to put those alleles, attach them to our chromosomes. Again, she's a female, so we need 2 X's, and both of them are going to be capital H. Again, she has no family history, so she does not have that recessive hemophilia allele. All right, moving down, a male with hemophilia. All right, so we know males are going to have at least 1 X. And because these are X-linked traits, when we say sex-linked, we almost always mean X-linked. Y chromosomes are very, very small compared to X chromosomes, so they don't have as much space for these extra traits. So almost always, more often than not, it will be on that X chromosome. All right, so our male with hemophilia, that means he's going to have a little h. Why? He only has 1 X chromosome, and that 1 X chromosome has to have that hemophilia allele on it. So at the top, we're going to make a little h there. And since it's a male, we're just going to stick in our Y chromosome. Because it is an X-linked chromosome, it's not going to be found on that Y. It's only found on the X because it is on the X chromosome. All right, next up, a male with muscular dystrophy. Again, muscular dystrophy is recessive, so it's going to be almost exactly like our hemophiliac, except we're going to use a little m for muscular dystrophy. All right, a male with normal color vision. Normal color vision. So again, we need to write in our X because males have that 1 X chromosome. And our alleles here, our traits for these various disorders, are found on this X chromosome. So if he's normal, normal means big C. And his Y chromosome. All right, moving over to the other side here, a normal color vision female with a color-blind father. So we need to draw our first X because she's going to have 2 of those. And if she has normal color vision with a colorblind father, That means she gets a normal allele from mom and a recessive allele from dad. So she has one of each. She's going to be heterozygous. So let's look over here. She's going to be one big H from mom, the normal gene, and the little h from dad. Oops, sorry. The little c from dad because he is colorblind. Everybody gets one allele from each parent. She gets the regular big C, the normal color vision from mom. And because her dad is colorblind, she's going to get the little allele there. Dad can only give her that one allele because looking over here, he only gets one allele. He doesn't have two, so there isn't a chance there for him to pass on any other allele besides that little one. And thinking about our best practices here, capital letters come before our lowercase letters, so I'm going to put the big C from mom first, and then the little c from dad second. I know C's are kind of hard to see the difference between capital and lowercase. I just try to make mine pretty disparate with their sizes when I'm handwriting. All right, next up, a male with normal blood clotting. So hemophilia is a lack in platelets or blood clotting factors, so that people with hemophilia, if they get cut or something, they bleed for much longer because their blood doesn't clot as quickly. So a male with normal blood clotting, he's going to have at least one X. And looking here, normal is capital H. Again, he only has that one X chromosome, so he only gets that one allele. Whatever he gets is what he gets from that X. Since he's normal, we get a capital H and a Y. Because he's a male, we get X and Y chromosomes. Lastly, here, a colorblind male. We need an X. What does colorblind look like? Little c. He only has that one X chromosome, so there's no chance in him being heterozygous. He must have that one single little c, and then his Y chromosome. All right, moving on. Number 2. Cross a female who is a carrier of the gene for hemophilia with a man who is normal blood clotting. Okay. What are the parent genotypes? We were given the phenotypes. Now we need to translate that into genotypes. All right, this is very archaic and I feel gross doing it, but using colors is always helpful. So I'm going to make males blue, females pink, just to make things clear and easy. Males are allowed to like pink, females are allowed to like blue. Just choosing these colors because they're associated with those whether we like it or not. All right, so what are our parent genotypes? Cross a female who is a carrier for the gene for hemophilia. So she's a carrier, meaning she's expressing the normal trait of not being hemophiliac, but she's carrying the gene for hemophilia. So she's going to have at least one X, we know this. And if she's a carrier, she's going to be heterozygous. She's carrying on one of those little H's, recessive genes for hemophilia, but she's expressing no hemophilia. So she's going to be heterozygous, meaning one of each capitalization. So she'll be X with a big H with an X and a little h. Okay, now she's getting with a man who is normal blood clotting. And a normal blood clotting means, hey, he's got that one X. On that X chromosome, we have our hemophilia. He is normal, so he gets a big H, and his other chromosome is a Y, where it doesn't have this hemophilia allele. All right, so our Punnett square now. We plug these into here. Things are gonna get a little bit more confusing now. Each of these chromosomes has an allele attached. Normally, we just put the alleles in our Punnett square here, but since these are sex-linked, we have to also bring in our sex chromosomes to our Punnett square. So best practice tells us males go across the top, females go down the side. Let's get our male in our Punnett square here. So we have to keep our chromosomes with our alleles. So that means his X will go here with a big H, and in the next column over are our Ys. There's no allele there because it is X linked. All right, next up is our female. We're gonna separate her X's. Whoops, I was looking at the H's. X, and the first one is a capital H. x and a lowercase h. Great. Now we've plugged into our Punnett square. Time to figure out our offspring here. All right. We are going to get the x with a big H from dad and an x with a big H from mom. All right, and then since x's come before y's, we're going to get an x with a big H from mom and a y from dad. Next up, we're going to get a big H from dad on that X chromosome and an X with a little h from mom. And lastly, X's again come before Y, so we're going to put our X with our little h there from mom and our Y chromosome from dad there. Okie dokie. Now we're going to get into our ratios. So genotypic and phenotypic ratios. This side will be our genotypes, this side will be our phenotypes. So just looking really quick at our offspring here. First, in this first box, we have two X's with two capital H's. So this will be a normal female. She's homozygous dominant. This top box here is homozygous dominant. So we have at least one. There's only one H there. We've got a heterozygote and one H there. So there's only going to be one of these guys. I guess I should say ladies. Next up is this heterozygote, XX. Here are two XX's. We did this one. Now we need to put in this one out of 4 of those. Next up, we have our heterozygous recessive. We don't have any of those here. Great, 0 out of 4 there. Now we're getting into our males. We have one male who's big, one male who's got the little h. So we have one of each of those going on there. If you like percentages, this is 25%, 25%, 0%, 25%, and 25%. That adds up to 100%. Perfect. All right, now we need to look at our phenotypes. I'm going to get out my trusty highlighters here and get some highlighting going. All right. So we need to determine whether or not our offspring are hemophiliac or normal. So looking at all of our genotypes here, if we see a big H, it's going to dominate, it's going to be the dominant trait, and that offspring will be normal. They will not be expressing that hemophiliac trait. So this one is heterozygous normal. There's at least homozygous normal. There's at least one big H. So that one will be yellow. This one, there's at least one big H. Great, normal. And this one, again, there's at least one big H. They will be normal as well. However, this little guy here, he's got only one X, and that one X happens to have the little h. So this dude is going to be a hemophiliac. Now we need to compare our phenotypes here with our descriptions, males and females. So how many are homozygous normal? This one up here, homozygous normal. None of the other ones are homozygous for capital. So there's 1 out of 4 of those. Heterozygous normal females. Got another one of those. She's heterozygous. She's normal because that big H will dominate. Females with hemophilia, not seeing any 2X, 2 little H's. So there's 0 of those. Normal males. Look at that. We got one of those. One of them has the big H, and the other male is the one with hemophilia. You like percentages? There's 25%, 25%, 0%, 25%, and 25%. Oops, sorry. It's already up to the side there. All right, so we did it. We figured out the Punnett square. We figured out the genotypic ratios and the phenotypic ratios. All right, moving on to number 3. All right, cross a female with normal color vision whose father was colorblind with a man who has color blindness. So our female here, she's going to have normal color vision, but her father was colorblind. And our male, who is colorblind. Male. All right. So what are their genotypes? We have their phenotypes given to us in the question. What is their genotype? So the male, he's going to have at least one X, and that colorblindness gene will be on the X chromosome. He is colorblind, so we need a little c. It is a recessive trait, and he has a Y chromosome or a second chromosome. The female, she has normal color vision, but if her father is colorblind, she is going to carry that colorblind trait or that allele. So that means on one of her X's, she needs to have the little one, but if she's normal, she has at least one dominant allele. So she's going to have a big C there and a little c there from her dad. Great, now let's plug them into our Punnett square. So best practices tell us males go across the top, females go down the side. Let's put our parents here into our Punnett square. So again, we're going to keep our chromosomes separated, and our allele is attached to our X chromosome. He gets a little c. And our female here, we're going to put an X in each one of these. She has 2 X chromosomes, and her alleles are one big C and one little c. So a big C there and a little c there. All right, now we get to fill out the inside where our offspring go. This first box, we're going to get a big C from mom and an X with a little c from dad. Next box, we're going to get a big C from mom and a Y from dad. Third box here, we're going to get a little c from mom and a little c from dad. In our last box here, another little c from mom and a Y from dad. Awesome, awesome. So let's take a look at our ratios now. Genotypic ratio coming up first. First up is a homozygous dominant. We're not seeing any big C's. So we got 0 out of 4 of those. Next up is a heterozygous female. Our first box here, we got a big C from mom and a little c from dad. This is a heterozygous female. She appears to be the only one. Our last female option here is a colorblind female, 2 recessive little c's. We got one of those. All right, now males. This first one is normal. He's a big C. Great, we got one of those. She got, mom gave us that big C there. And lastly, we have a colorblind male. We get one in this last box here. We get the little c from mom and the Y from dad. 1 out of 4 there. If you like percentages, 0%, 25%, 25%, and 25%. All right, let's look at our genotypes. Again, I'm going to try to use some colors to help us out here. What did I use last time? Yellow is normal, orange is afflicted. So if there's at least one big C, they will be normal. So these top 2 here, they have at least one big C, they'll be normal. Cool, cool, cool. They can see all the colors. Then this one at the bottom, we're getting little c, they will be colorblind. And this one here, there's only one X, only one C allele, and it happens to be small. That means, sadly, they'll be colorblind as well. All right, now let's look at our phenotypic ratios. Homozygous normal females. Well, we didn't have any of those. We have no 2 X's, 2 big C's, so we got 0 of those. Heterozygous females, we got one of those. She is normal. She has at least one big C. Colorblind females, hey, we got one of those. She got a little C from each parent. Normal males, this top one up here is going to be normal. And our colorblind males, again, this one is colorblind because they have one little C and a Y, meaning they cannot be heterozygous. Whatever C they get is the C that they get. Percentages. All right. All right, we're going to move on to our last one here, number 4. Cross a woman who does not suffer from muscular dystrophy, so not, and has no family history with a man who has the disorder. So this man has the disorder. Okie doke. So our female, she does not have it. Whoops. She does not have it, and she has no family history, meaning she doesn't have that recessive allele for muscular dystrophy because nobody has it. She can't get it if she hasn't had that gene passed down to her. So first up, we know she's going to have 2 X's. If there's no family history, she gets capital M's because not having it is dominant. Now our man, he has the disorder. So he gets his 2 sex chromosomes. If he has it, he gets that little lowercase m for that recessive allele. All right, let's plug it into our Punnett square here. We have our male, the little m, and he gets a Y. This female is homozygous dominant, so both of her X's go there. Capital M, capital M. All right, first box here. This kid gets a X with a capital M from mom, and an X with a little m from dad. This kid gets capital M from mom, and a Y from dad. This kid gets an X with a capital M from mom, and an X with a little m from dad. Oh, they're starting to get very similar looking. I apologize. This kid gets an X, a capital M from mom, and a Y from dad. All right, now I have to do a little interesting paper shuffle here. I'm going to finish out our ratios. All right, there we go. So looking at our genotypes here, well, these should be M's. I will change that on yours. It's a learning process, copy and paste. It's Ratliff, big and little m, little m, big and little m. All right. So first up, we have a homozygous dominant female. So looking at our 2 females, neither of them are homozygous dominant. Then we're going to look at our heterozygous females. Our 2 females, they each get 1 big M from mom and 1 little m from dad. So we have 2 of those. All right, now our homozygous recessive females, we are out of females because they're both heterozygous. Next up, our males. Well, both of these males got capital M's from mom. So we got 2 of those, and we don't have any recessive males. We're out of males. So percentages. All right. Now our last little bit, let's figure out our phenotypes. Our normal guys and gals here. So because there's at least 1 big M here, they will be normal, 1 big M there, normal. And these guys each got a big M from mom there. They will be normal as well. So all of these kids will end up being normal. let's look at their spread in terms of breaking down all of these words: heterozygous, homozygous, males, females, muscular dystrophy. All right, homozygous normal females. Well, we don't have any homozygous dominants, so we got 0 of those. Heterozygous normal females, we got 2 of those. Females with muscular dystrophy, since both of our females were dominant, none had this disease. Normal males, again, we have 2 of those because they each got a big M from mom, meaning we have no males left, and they have none of them have muscular dystrophy. Percentages. And there we go. We finished up sex-linked traits. I hope this was helpful. Stick around for my next video.